What we're going to do now is we're going to, as I said, shift gears, and we're going to start talking about association rules. So, the first thing we want to know is what's the difference between classification and association rule learning. So, the main difference is we're going to, instead of classify objects using the attributes to actually classify objects, what we're going to look at is trying to find interesting relationships between our attributes. So an example of this that we mentioned early on in the semester was the example of the Midwest supermarket chain that went through their data and just happened to notice that a lot of purchasers of diapers also happened to purchase beer. So and so the classic application that we're going to discuss, and we're not going to get through the whole algorithm that the first algorithm we're going to talk about, and maybe it's the only algorithm we'll talk about with association rule learning today, but we'll get started on it. So the classic application is market basket analysis. That's the example where we're going to look at all of our transactions and basically list everything that was, say, purchased, put into the market, and then try to find commonalities between those. So we're going to start off with a formalism. We're going to start off with a basic model. So I is going to be, and those double reverse arrows somehow PowerPoint yeah, translates ... I keep forgetting about that into those weird arrows, but we have items I1, I2 up through IM. It's just a set of items. We'll go through an example. And what we're looking for is going to be some association rule, which is going to be a rule from one item set to another item set. So X and Y are both subsets of this item, of the original item set, and they're disjoint. So they have nothing in common. So some definitions. We're going to be interested in what's called the support, sometimes also called the coverage of a rule, or of a set. That's a fraction of transactions that contains a particular item set. And then we're also going to be looking at the confidence, or also called the accuracy, and that's a fraction of transactions that contains X that also contains the other set, Y. So, and we'll, as I said, we'll go through an example and we'll see exactly what we mean by these definitions. But essentially, one of the things that we're going to be really interested in are only those item sets item sets with high support. Those transactions that occur frequently, basically, because if you don't have a lot of transactions, items being purchased, then there's not really a business case for it. You're not going to make a lot of money if you have like 1 or 2 sold per year. So you want relatively high support, and so our goal is going to be to find rules, and again, this should become clearer as we go through this, where we have support above some minimum threshold and the confidence above some minimum threshold as well.
So what is sup and what's conf?
Sup is support and conf is confidence.
Oh,
it's just, okay. I didn't want to write them.
Okay.
So those are the two thresholds. Min sup will be like your threshold for your smallest support. Min conf could be the threshold for your smallest confidence that you're going to be looking at. So, suppose you have a whole bunch, I mean, not even that many transactions in your items set. So one way to get these rules is brute force, which means list all of your association rules, compute the support and confidence for each rule, and then eliminate rules failing to meet thresholds. Now, this isn't going to be very practical, and I want you to tell me why. James.
Computationally expensive.
Why?
Because if you're doing, say, with 10,000 records, you've got to go through 10,000 possibilities for each record.
Okay. Drew, you're in discrete concepts. Maybe you can even be a little more explicit about that. Suppose you have a set of size 10, right? Now, we're looking at subsets of our item set, right? X and Y are subsets of our item set. And we're looking at rules from one subset into another. So suppose our item set has 10 items. How many possible subsets are there? Of the item set.
Oh, isn't it 2 to the n?
Okay, so that includes the empty set. So if we exclude the empty set, because that's not something we're interested in, it would be 2 to the number, the size of our item set minus 1. So it's going to, and if you notice that, that has exponential growth in the size of the item set. I just clicked and nothing happened. So here's the reason. We could actually go through where all this comes from, but the number of possible rules, because remember I'm going from one item set into the other item set, is given by this formula that I threw up here, right? You've got a summation, right? Your one item set will call the size of your one subset can go up to size d minus 1, so that your second subset has to always have 1 as well. So your sum goes from 1 to d minus 1. Remember, you're going from one subset into another one. So you've got the summation, the size of your item set, choose your size of your other, and the upshot is, notice, it's 3 to the size of your original item set, minus 2 to the size plus 1, plus 1. And you can see the growth here pretty fast. And even if you don't even have 10,000 records,
you wouldn't want to with that formula.
You wouldn't even want to with that formula, right? So you were correct, it's computationally very expensive. But you were off in perhaps the reasoning exactly. Does that make sense? But I mean, the key point is still the same, that even at 10, we're at 6,000 possible rules. And that's only with like a supermarket with 10 items that it carries.
It's like a gas station in the middle.
It's like, so,
Milk egg spread.
pardon?
I said milk egg spread.
Okay. Oh, wait, you're gonna, you forgot beer.
Oh,
Yeah, don't carry that one.
and diapers. There's 5.
No, we don't have, I can't remember what the eggs, I think is in our market basket, but. So, here's the main problem, the number of candidate item sets, n equals, oh, it's 2 to the d minus 1 is a possible number of item sets. So that got superscripted there. The 2 should be down below. 2 to the d minus 1 is the number of candidate sets. And here you can look, this is called an item set lattice. So if you have a possibility of having 5 items, these are all of our possible item sets. Here we are including the null set, the empty set. And so this is all 32 possible subsets. But the relationship here is, for example, A is a subset of A, B, A, C. So the lines indicate what's a subset of other sets. And that's going to help us analyze and go through the first algorithm that we will develop here. So, and this is pretty much taken straight from the text in this example. So here's an example. I guess there's another item, right? So here we've got 5 transactions. The first person bought bread and milk. Second transaction was bread, diaper, beer, and eggs. Milk, I guess diapers are in here. Milk, diaper, beer, and Coke, and so on, right? So the first thing we want to look at is we're going to try to go from here into a list of candidates of our rules.
Can't you also associate bread with milk?
So the first thing we want to do, since we're going to try to simplify everything, is to use, and this is going to be our primary algorithm as we get started here. It's called the a priori principle. It's based on the a priori principle. And the idea here is that if an item set is frequent, then so are its subsets. And the reason for this is because if the support of an item set can never exceed the support of its subsets. So if we go back to our, right? So here we've got an item set here. Bread, the number 5 is bread, milk, diaper, Coke, right? And you look at that and there's only one example with bread, milk, diaper, and Coke, right? But its subsets have higher support, right? Bread, milk, diaper, you see twice here.
Bread and milk, you see 3 times.
Bread, milk, you see 3 times, and so on. So that's the principle we're going to try to take advantage of here.
Oh.
But we're going to take advantage of it, and we'll see it exactly, kind of in a certain sense in reverse. But it's like an anti-monotone property. If everyone's familiar with monotonicity in mathematics, So if x is less than y, then f of x is less than f of y, right? So that's a monotone property. Here it's the reverse of that. Basically, x less than y, now f of x is greater, larger, so it's a negative direction there, negative property. So, here's the idea. We're going to, as I said, we're going to use that property, but we're going to reverse it, right? Because I said, basically we're going to look at the smaller subset, the subsets. And if those subsets are infrequent, then all the supersets are also infrequent. So say this item set that contains only the items A and B. If that's not very frequent, then neither can be ABC or ABD. Because remember, subsets, AB is a subset of ABC. ABC cannot have more support than AB. So if AB is not frequent, or if the support of AB is low, then below our threshold, right? Then so are all these circled in red subsets, or item sets. So we can prune those out, eliminate those from consideration. So basically this is going to be an ongoing process of seeing how much we can eliminate as we go through. What?
In this case, that's like a quarter of your set.
A quarter of our set. And it depends, I mean.
Well, I mean, but that's a lot of time savings.
That's a lot of time savings. But, I don't know. If it's 2 to the 1,000, right? Hey, you've saved a lot of time, but you still have a long way to go, right? So you have to be, so even if you saved a quarter of 2 to the 1,000, you're still stuck with a huge problem. Yeah?
What if you go with the reverse, rather than pruning things that are infrequent, only focus on things that are frequent?
Well, I mean, that's essentially what we're going to do.
Okay, so you just keep applying this until you reach like a threshold.
Right, and so, I mean, you can, obviously, the higher that minimum threshold is, right? If your threshold is high, then you can probably cut out a whole bunch more stuff, but now you might be cutting out interesting rules that you might be interested in as well. A trade-off, right? So let's, I bring that up here. I wanted to recall our example. Here are our transactions. And let's suppose we have our minimum support level of 3 out of the, whatever, 6 items. I can't, how many do we have? It looks like 6 items. So what that 3 means, though, is that, for example, here, bread appears 4 times. So bread by itself is above our threshold. Milk appears 4 times. Diaper appears 4 times. Beer 3. Coke twice.
Okay, so it's gone.
So we're going to get rid of Coke. And we're going to get rid of eggs. Right? So we're going to, we're going to call K item sets. The K here is like I can look at 1 item sets. That's going to be an item set with 1 item. 2 item set will be an item set with 2 items. let's take a look. I'm not seeing any questions. So here we have it. Okay? And we'll see how, again, we can start pruning it. So we just went through that. Coke and eggs, gone. Right? In our one item set. And so what that means now is we're only going to start looking, so because Coke and eggs are gone, we're now going to start looking at our two item sets. Okay? Our two item sets are not going to include Coke or eggs. We've eliminated Coke or eggs. So as we go up a level, so to speak, I'm not even going to consider bread and Coke. So it's going to help with not just eliminating these one item sets, but also eliminating our two item sets. Right? So if we look at it, we have bread and milk, bread and beer, bread and diapers, milk and beer, milk and diapers, and beer and diapers. We've cut the number down to 4 items, right? And basically the number of groups with 4 items, the number of combinations, we see it right here, is 6. The number of subsets with just exactly those 4 items. And we again now look at these 2 item subsets. So if we look at bread and milk, we want to count the number. Where's bread and milk? We see bread and milk appears once in transaction 1, it appears in 4, and it appears in 5. So our count is 3. Whereas bread and diapers is also 3 in transaction 2, 4, and 5.
Beer and diapers
Beer and diapers
is 3.
is it 3?
2, 3, and 4.
Oh, 2, 3, and 4. We don't want to look at eggs or Coke, but if we look at, I'm trying to find the small one. Milk and diapers. Milk and diapers we only see in 4 and 5.
No, we don't.
And
See,
3.
Oh, 3, 4, and 5. What was the other one?
Bread and diaper would be small.
Bread and diaper is 3.
Milk and milk.
Beer and
Milk and beer?
that's 2.
Milk and beer only appears twice.
Always makes beer and milk. That's not.
So, and that's what we see here, and the other one is bread and beer appeared twice. So we had bread and beer and milk and beer appeared twice. So when we go to the 3 item subset, we're going to eliminate the ones with bread and beer and milk and beer, just like we eliminated there. We're not going to look at those triples that include bread beer and milk beer, right? So we're going to look at triples that contain bread, milk, and diapers, and there's only 1. Because if you take these 2 out, all these 4 other remaining transactions all are part of the triple bread, milk, diaper. They're subsets of bread, milk, diaper. So here, just like you were saying about a 4th, notice we went from a possibility of 6 choose 1 item sets, 6 choose 2 item sets, and 6 through 3 item sets. A total of 41 possible item sets to consider, down to 13. So the 13 being 4 choose, basically you get 4 choose 2 for your, I worked that out. 4 choose 2 comes, and then, I'm trying to remember exactly where that came from. Okay, so let's go to the actual algorithm. So is that kind of, I mean, that's the basic idea, the first part here. So we're going to say, start with k equals 1. We're going to generate frequent item sets of length 1. Right? So the 1 item sets, like we just did. And now what we're going to do is we're going to repeat until we can find no new frequent item sets. So the idea is from our length k item sets, we're going to look at candidate k plus 1. So the next larger size. So kind of like what we did here. Here we started with 1 item sets. We eliminated the ones without enough support, and we only considered the remaining ones to generate the 2 item sets. Right? And so you can see the process here. Here we eliminated the ones without the required support and only kept the ones with the required support, and the only k, in this case k is 2, the only 3 item sets we consider are the ones that have what's remaining as subsets. So at each stage we're generating our item subsets from the previous stage, and then we count their support. We prune, and I think you can see it right here. We pruned, we generated the next generation, the next larger size sets. We pruned that, we generate the next larger size set, we prune that. And now once you're here, you don't have anywhere to go, right? Yeah,
So since the beer isn't, okay, so we throw out the beer with the bread and beer and the milk and beer.
Right?
So the beer and diaper doesn't get put into our three.
Not in this example, right?
Okay, so we're gonna have another example where we have a variable thrown out in a 2 item set, but it still correlates with 3. Like a different one?
Well, if it gets thrown out,
That's
well, it could have been, I mean, so this example just isn't, I mean, if I came up with another example, you could end up with maybe 2 things down here, and maybe now you need to go to a 4 item subset, maybe that.
Okay, well, just from this, it looks like any elements of that set that you throw out, like any other set containing an element that has been thrown out, you will throw out that set also.
Right.
Okay.
So here I'm throwing out the set bread and beer, but when I did that, you're saying I've thrown out beer.
Right, that's what I'm saying.
And that's, I think, just the kind of an artifact of this example.
Okay.
Because if I had thrown out, maybe milk and beer, if I had had another transaction, milk and beer would have been 3, in which case now there would have been 4 items, and I would have had to consider possibly another 3 item subset.
Okay, and then...
So I think it's more an artifact of this particular example.
Okay. Okay.
So basically that's all that this is happening here. you generate the next level, you prune the candidate item sets of the previous level, you count the support of each candidate, you eliminate your infrequent candidates at each stage. So, but this still, there's still, if we go back up to that as well, there's still a lot of work that's hidden underneath, okay? And so now we're kind of diving into this algorithm in a little more depth. Because right here, on the very first step, it says generate the next larger item sets, right? You have your K frequent item sets of length 1, and now you're generating those item sets of length 2, or you have your length 2 and you want to generate all the item sets of length 3. And the problem is, when K is small, as in this example, it's easy to do. But say K is 100, let's just still keep things relatively small. How can you generate your item sets that contain all of these subsets of size 100? You want to look at supersets of size 101. You want to look at all of those supersets of size 101 that contain all these subsets of size 100. So as the K gets large, how do you generate? And it's going to depend on also how many items are originally in your superset. I mean, in your original
Item set.
kind of universal item set. Say that's 10,000. You're just looking to go from 100 to 101. But you still have quite a huge computational difficulty in front of you. Does that make sense? And these numbers are not that large that I'm throwing around here. You think of a standard supermarket, it's not, they don't even have just hundreds of items,
A couple thousand items.
right? So, I hope that's large enough. I don't know if everyone can see here, but this one possible method is, again, brute force. But this is just brute force for the candidate generation. So here we've got our items: beer, bread, cola, diapers, milk, eggs. And we want to generate, say, in this case, we're going to generate all of the subsets of size 3. And there end up being 20 right here. 6 choose 3. And from that, you're going to prune by counting your support for all of those to get bread, diapers, milk. So that would be a brute force. Here we're going directly from our items to our 3. A better approach is what's called the FK-1 cross FK method. And so let's take a look at how this works. Here, notice I've got my 1 item sets. I've pruned them, so we're down to 4 here. So beer, bread, diapers, and milk. we've got our frequent two item set. So we've generated that two item set. Should I back up to where we saw that before? So here's our two item sets. We had bread milk, bread diaper, milk diaper, and beer diaper. Right, the ones we didn't have were bread beer and milk beer. So if we look at that, so here's those four again. And now what we're going to do is just kind of combine the one item sets and the two item sets to get our three item sets. So we'll throw beer in, beer and diapers is beer, but so beer, bread, and diapers. So that's the first one. Beer, bread, and milk is the last one. And just going through examples, if I start with bread as my one item set, we do bread, diapers, milk, or bread, beer, diapers. So that's how we're going to generate our three item subsets. We're just going to take like a cross product and or union. Essentially, we're going to union these two, the items of my one item subsets and the two item subsets, to try to get my three item subsets. And if it only ends up when you union it that you end up with two, you don't even look at it.
So most of the time, like this, it only applies for this example that we end up with 4 new sets, right?
Right.
We should expect to see more.
Well, this is going to depend on how many items, how many transactions you're looking at,
Right.
how many, right. So for examples, their examples are by default
Right.
toy problems, right? It's more so you understand the process,
Concepts.
the concept of the thought process of how can we do this? How can we simplify all that computational complexity? Because, and it's more just the idea behind the algorithm. And because if you do end up going into, say, data mining, what's important is inventing these algorithms to try to simplify the computational complexity. And that's where a lot of the hard work goes. You want accuracy, you want speed. So it's not just playing around. The hard part's coming up with, well, what's the original idea here? How can we handle tens of thousands of items, right? But if you can understand what's going on here, then and try to scale that up to large numbers of items. Does that? And so, I mean, if we're trying to understand it, we have to be working with toy examples.
Right. Just
If I threw out a real world, we can't even, you saw that in the UCI homework assignment, some of those data sets, you can't even look at them and try to understand what's going on. Right? But here we're understanding the idea behind the algorithm, and so you can see how you're cutting down, and maybe it will work, maybe it won't work. The only way for you to really determine that is to actually experiment with it. It could be a great idea and just not work.
right.
And this is pretty much a similar concept. It's FK -1. So here, to get a 3-item subset, what you're doing is you're taking all your 2-item subsets, unioning them together, unioning them together, right? To get a 3-item, to get your 3-item subsets, and then you prune. And that's what we still have some other issues that we'll talk about next time in this algorithm. For example, so far we've just generated our candidates. Now we need to also go through all our records and try to count the support of each of our candidates. And how can we simplify that process? So I'll leave it there. There's some multiple ideas that we can come up with. So let's